My name is Dave Olarte. I'm part of the medical informatics team, and this is Giving the Bird to Python. This story started a long time ago. In 1965 in Miami, Florida, I was one of 5 children. I am one of 5 children, and my family was on a rare vacation, having traveled from New Jersey to Miami, Florida to visit my retired grandparents. Parrot Jungle was sort of like a zoo with only parrots in it. As I recall, it was really loud and not very interesting. But we did get to see a parrot pretty much eat a guy's tonsils, and that was a little cool. They said it would be fun. Fun, fun, fun. Get your picture taken with the parrots. You could pose for pictures with a parrot or 2 on your arm for a price. And here we are, getting our picture taken with the parrots. Notice that everyone else is smiling. But at the last moment, my grandfather told me, if you don't hold still, it'll peck your eye out. That's not a happy look on my face. It's a get this thing the hell off my arm look. This is shot from the 5th floor of the Aquafy building, looking out over the roof of green. I believe they're searching for my eyes. So this is my revenge on the birds. I have notes here to take a drink because I'll go too fast. So take a drink. The tools, just a Mac, a webcam, and some open source software. It's an older Mac running older Lion. It's not the latest and greatest webcam. I think it's a 1080p, but it might be 720, I'm not sure. The latest Python, the latest OpenCV. Why Python? Just like Ruby, Python's a lot of fun to play with. Performance wasn't an issue, and it's got great scientific support. Research, colleges, universities, they use it a lot, and there's great scientific support. NumPy, SciPy for matrix and linear algebra. Scikit-learn, which was covered in at least one other presentation for machine learning. OpenCV for computer vision, does lots of nifty stuff, zooms, image adjusts, more than I can say here. It's got great online support, and specifically, it has a full Python interface. It is also used heavily in research, and it's fast. And in my opinion, it makes video and digital image manipulation simple, something that in the past I'd experienced was very hard to do. Today we have a multitude of image formats, and what's shown here is just well-used formats. An example is the JPEG format. It's not simple, and I didn't want to mess with image formats. I just wanted to find birds. So to OpenCV and Python, an image is just a matrix of pixels, regardless of what kind of image it is. JPEG, BMP, it doesn't matter. It's just a matrix. There's a multitude of video formats also, and each one is more complex than JPEG. And this presentation was supposed to keep scrolling to show you more, but I haven't mastered PowerPoint yet. I only put this in here because I thought it was a cool emoticon. All right, video in OpenCV, it's all just a matrix, the same as an image was, a NumPy matrix. Each frame, as you read it in from the file, becomes a matrix identical to the image matrix. This was taken at Gatorland I'm told that we went there prior to going to Parrot Jungle. This may explain why I was told that the parrot would peck my eye out. That's me. Okay, now for the Python. To read and display an image in Python using OpenCV is just 4 statements, 2 of which are just kind of extra code. So you'll see the pattern image read, image show a lot. And I'm going to switch back and forth to the PyCharm IDE, so put up with it because I can't see it when it switches. So I have to trust. I don't like trusting. And I'm doing this to prove that I'm not a liar. So this is the code. And I have to switch once again to pop up the Python window. So 4 lines of code to show an image. Next, we'll read and display a video file. And I told you that a video file is just a file full of images. So here's the proof. Actually, here's the code. 2 extra lines of code. One to define the file, and the next to open and read it. And below it is the same old image read, image show. Blind faith here. Notice that the first line, I'm ad-libbing this now, you see assist.argv, and it's taken the file name from the command that I used to start this program. I was supposed to, blind trust again. I wanted to bring up one line, and it's an OpenCV statement that'll wait for keyboard input from the keyboard, or wait the number of milliseconds I put there. You'll see that as a pattern throughout this too. It also checks to see if it was a Q key so that I can close that Python window and shut down the Python program. All right, and then there's reading and displaying live video. It's the same code except for the argument of 0 instead of the file name that I passed before. The webcam's right here, and the video's right there, live. So that's 6 or 8 lines of code. Okay, so the first challenge between me and the birds is I'm pointing a webcam out the window, and I want to find the bird in the image that I'm capturing, the live stream. This is where my camera is located, pointing out the window right next to my cube. And from the outside, this is the approximate location of my window. So we have an image. This seems like an easy problem. You think about the sky, and you don't really see anything up in it except for birds and clouds and sky. So if there's something in the sky, I hope it's going to be a bird. Sometimes it's a helicopter. But there's a problem because images have lots of pixels, lots, megapixels, millions. So finding one tiny bird among all those pixels, along with the lighting glare and the clouds clouding up the picture, it's a needle in a haystack. So the first thing I do, there's an old, I'm ad-libbing again. There's an old saying, if you want to find the quickest way to do something, you give it to a lazy man. And I'm a lazy man, which is why you don't see many words on these slides. So the first thing I'm going to do is get rid of all the noise so that I can, all I care about is there something up there? I don't care about what kind it is, what it is, color, it doesn't matter. So I've decided to say everything except for the bird is noise. Clouds, glare, it's all noise. So the contrast between clouds and sky, and the glare, let me switch back to that picture for a second. Clouds and sky, clouds and glare, which is, if I remember my pen here, it's that glare. If you look at the contrasting edges there, it's low. There's not a lot of contrast. So I'm going to look for edges of serious contrast. And here's an example. The original picture, and of course, the edges that are detected by an edge detection algorithm. OpenCV has a built-in edge detection algorithm. You pass in an image, and it returns a binary image where non-black pixels are edges. So back to my code, you see the image read, the image show, and then I wedged in between it the call to the edge detection, which uses the canny algorithm, so they call it canny. The 10 and the 30 are thresholds, and I'll demonstrate this live, even though it's not very exciting. So everything is 0 or black except for what this algorithm came up with for edges. Got to be sure and quit that each time. Here you can see the edges of the bird are detected. However, there are lots of artifacts beside the bird, the glare from the windows, and even some clouds. And that, my notes are duplicated there. Okay, so we're going to up the parameters that we can change on this canny call. And it worked. I got rid of all the edges, all the noise, and all I see is the edges outlined of a bird. And then I try it with a different image because that was an image on a cloudy day, and this is an image, even though it doesn't really show it, it's actually a bright blue sky, but the webcam is doing its white balance kind of funny. And this is what I got. I got the stupid glare from the office lights. I wish those were, that would have made things a lot easier. So even cranking up the thresholds on the canny algorithm, the edge detection algorithm, doesn't get rid of the artifacts. Rats. So the lazy man approach, I'm going to brighten the picture so that the bright sky is still bright and the clouds are really bright now, so that there's no difference between the clouds and the bright sky. And the white from the light glare from inside is also as bright as the clouds. So the idea is to get rid of the contrast between the things that are white. An image is just a matrix of numbers ranging from 0 to 255. So to overexpose, I just add a uniform value to each one of the cells in the matrix. So whites are still white, but grays become white too, and blacks are still dark in comparison. Demonstrate. That wasn't right. Sorry, I ran the wrong one. So now, the glare from the window is gone. So this is the three pictures that I started. In the upper left is the image I started with. In the lower left is the brightened image, where you can see the glare from the office lights is just barely noticeable now. And then the image on the right is the edge-detected image, and there are no noisy artifacts now. Once again, the edge image is just a binary image. Zeros are black and 1 is white, and there's no in between. So when we find an edge, it's a pixel value of 1. So determining if there's a bird is now easy. I just add up all these cells in the matrix, and if the number is more than 0, there was a bird there. So I wrote a little program that would, these are the images that I'll use to do just that very thing. I'm saying a lot now, don't do that. To demonstrate that I can find birds using edge detection and brightness. It doesn't do any good to run this one because you'd see the same output. It's just command line output. But I've named 3 images, bird 1, 2, and 3, that I showed you on the previous slide that had birds in them, and the other ones are named no bird 1, 2, and 3. And the program returned that the bird images did indeed have a bird in them, and it did not detect a bird in the ones that shouldn't have had a bird in it. This is Halloween the same year, and if you look close at the picture, it's pretty close that the bird had an effect on me. All right, so now we'll get on to the fun stuff, machine learning. I actually promised neural networks, and we're not going to do that. But we're going to find out where the bird's going to go next. And there's an end goal, but for now, we just want to, given we know where the bird was, where is it going to be next? So step 1 is we're just going to draw a box around the bird or object. That takes 3 more lines of code. The first one is an OpenCV routine to find all the contours in the image. The definition they gave of a contour is the dominant points on a digital curve. Essentially, it tries to describe the edge in fewer XY coordinates than the edges described originally. The bounding rectangle is another OpenCV procedure that will simply draw a rectangle around the edge that I passed. And this is called a bounding box. Just a blue box around the bird. Next, we'll, on a canned video, since we don't have live video with a bird in it, we want to do the same thing. And it's the same code that I added to the display video example that I showed you before. This one is showing, there are 2 birds in this short video clip, and it's showing them in real time. So this is how fast the birds that are close to my window actually fly. And it's successfully drawn a bounding box around them. It's using almost no CPU too, so that's nice. Oh, and I suspect around, this is at the Innovations campus, and in the west entrance, they've been building a new driveway. And I noticed there used to be a lot of crows during this winter that would perch on that ledge. And I thought, man, I'll just edge detect for crows. And there weren't any crows once they started the construction, but I noticed a lot of hawks just circling overhead. And the only birds I saw fly by were like rockets. They'd move really fast, and they never perched on that ledge anymore. So we suspect that it's because the hawks were hunting and the birds didn't want to become the object, their targets. So they're running for their lives. Good for them. Okay, so now the machine learning. If we know where the bird's flown, we can use that to guess where it'll fly next. For example, if it was at coordinates, Cartesian coordinates 0, 0, then 1, 1, then 2, 2, then our human guess is that it will be at 3, 3 next. So superimposing the videos of this bird flying, you can see that it's flying in a path. We have the XY coordinates of those, so we're going to capture those and then transmogrify them into data that we can use in our machine learning. So the XY coordinates to me, well, they were interesting, but they weren't useful. I'm more interested in not where the bird is next, but which direction he moved next, he or she moved next. So in this example, the yellow line should represent the x-axis for each frame-to-frame movement, and the red line, or the orange line, is really the change in angle from frame 1 to frame 2. So we're really interested in the angle of change between frame 1 and frame 2 and frame 3, and so on. And this is based on my supposition that birds change angles quickly, but they don't change speed quickly. Because I think if they change speed quickly, they'd like fall out of the sky. So I'm not sure I've supported that with my results in the end, but so I threw away their speed and just measured their angle. Okay, so specifically what I'm looking for is over a sequence of frames, their change in angle, and then I'll take the last change in angle. So I'm considering a sequence of 3 angle changes, and then the fourth one is my answer. So if they moved from 1 to 2 to 3 in angle change, then 4 will be the answer to what's the angle change going to be next. And it's a moving window, so throughout this bird's path, I'll produce 3 sets of data, the first 3 columns of which will be the features, and the last one will be either the target or the truth. So I'm building up data to train my algorithm. And wavy, this is what it's actually the polar coordinates, it's actually the phi value, the angle part of a polar coordinate. So hand wavy, timey, take a drink. And then I come up with this data, where the y angle is considered the answer if the inputs were angle 1, 2, and 3. And technically, angle 1, 2, and 3 are called the features, and the y angle is called the target or truth. So we'll do just a little bit of math, and this is, I think, junior high math. The coordinates for to define a straight line, y equals mx plus b, where you have a pair of xy coordinates. I'd rather call it y equals a function of x, where x is a feature that we pass, and y is the target variable, or the answer. So a little harder is a whole mess of x's and y's, and I want an equation that will best define a line that comes closest to the most xy coordinates. And that's called simple linear regression. But it's still a y equals fx function, except we're not just passing one x to get one y, we're passing a whole column of x's to get back a whole column of y's. And then it got harder, because we don't just have x, y, we have x, y, a, b, c, d, e, f, g. We pass a whole mess of variables to get out a single y, and that's called multivariate linear regression. And that's machine learning. That's one algorithm that you can use for machine learning. When you have a whole mess of variables and you want one answer. So I'm using, from scikit-learn, the linear regression model. The columns in my training data, the x angle 1, angle 2, angle 3, become a matrix with each column being angle 1, angle 2, or angle 3. And then this was the hard part to explain. So I'm passing it a matrix filled with features, angle 1, angle 2, angle 3. And I'm also passing it the angle y, or the truth. And I use that to train this algorithm, or for this, to train it. We'll just leave it with that. And then, so you see the linear regression algorithm.fit. That's actually the training portion, just that one line. And then the last line is that I will save that trained algorithm to disk, so I can use it later. So the actual training took just less than a second, and it was boring, and you wouldn't see anything by me running it, so I'm going to skip that part. So now I'd like to predict where the bird's going to fly next, given that it's already flown somewhere. I want to find where it flies next. And I've trained an algorithm to say, given angle 1, angle 2, angle 3, what's the next angle that's going to show up. So in the live feed or the canned feed from the file, I will do the same thing. I will find successive frames of a bird's flight, come up with the feature angles, but I won't come up with the truth or the target variable. And I will feed that to the same algorithm that I read in. I'll feed in the X matrix that I built. It's actually only got one row in it, but 3 columns of angle 1, angle 2, angle 3. And I'll get back a predicted angle from that. So that was it, to do the machine. The hard part of doing all that was building up the training data set and figuring out how to form those attributes in the right way that I could machine learn on them. So the machine learning code was actually easy. All right, so I have a live example, and I think this is where it's interesting if it runs. The code's not interesting to look at. Well, maybe it is. So a little explanation is, let me pause it. You can't, I stopped it in the wrong place. You can't see the bird, but this little crosshair represents it represents my prediction. If the crosshair is small, the circle around the crosshair is small, it means that I'm within 10 pixels of where the bird actually is with my prediction of where it would be. The green line is where the bird actually flew. The red line is where I predicted it would fly. So I'm slowing it down, really slow. And you can see, this is a really great one, the bird coming down. You can see that my algorithm is predicting where the bird's going to be pretty well, since that crosshair and it missed it. The bird's zigging, and my algorithm didn't do well on predicting the zig. Once again, I slowed this down, though, so that's real time. And it does all right as it's tracing the path of this very distant bird. And they fly pretty freaking fast. It's amazing. And yeah, I like that one. And it repeats over and over again, the same 19 birds or 21 birds. Let me speed it up to get to, I wanted to point out one. Okay, it's going to crash. Ignore that. Let's go back to the slide. Okay, let's see. Fooled you. Yeah, I fooled you. It's going to crash in here. This wasn't supposed to happen. Okay. Now, you saw the data. I had 21 rows of training data. That's not very much training data. Sorry, I had training data for 21 birds, which isn't very much if you're going to predict a whole mess of birds doing random flight. And yet, my algorithm, or the trained algorithm, was pretty darn accurate, in my opinion, of tracking the bird's flight. So I cheated because it looked a lot better when I was demoing it to you guys. The video that I extracted the data to train on was the same one that I just showed you to predict on. So when I trained the algorithm, it was an expert at that video. It knew everything. I mean, how good of an algorithm would it be if it couldn't predict anything on the algorithm that it trained on? So you would never want to do that in real life because you're never going to encounter data that you're training on. You're going to encounter a lot of variable data. And this is called overtraining, and it's a really bad thing, and it's a trap that you can get into easily when you're competing on the web. What was the name of the website? Kaggle. If you're doing a Kaggle competition like I did, and you train on data, and you think you've got a great algorithm, and then you submit it, and you do really poorly in the contest, that's a harsh reminder of the fact that you shouldn't overtrain. At any rate, so here it is. This is really my revenge on the birds. With a few extra lines of code. Oh, you guys are reading ahead on this. All right, so no crosshairs, right? I think it's H for help. Okay, help. I have a laser. If I press the L key, it's going to fire a laser. It's going to fire a laser at where I predict the bird's going to be next. And once again, the green path's actual, red path's predicted, large crosshairs your way out. Oh, but there are no crosshairs in this. So I don't know. See, my prediction was accurate. So this is like a self-guided laser based on this trained algorithm. Oh, and I can nail it every time here. Yeah, that's where it zigged around a little bit, and little bastard. All right, so you get the idea. Need to see 32 minutes, so I'm okay. Well, I've added code to this, and I'm scrolling through it, and you're not really supposed to read it, not because there's all kinds of extra magic stuff in there. It was very simple to do. It took me probably 5 minutes to add the laser shooting stuff to it, and it's probably 8 lines of code to do that. So Python made it really fun to play around with this stuff. And these are my boys. I had to pass on the tradition, but I did not tell them it would peck their eyes out. And that's really the end of my talk. Now, I do have one video that I'll leave you with, one example, and that is I really reached out, took the chance. This is a video with 313 birds that I counted through it, and the same poorly trained algorithm is going to predict against these birds that I've never seen before. I won't shoot lasers. Once again, the small crosshairs are when it's accurate. You'll notice that sometimes you see a green line and you don't see any red line and you don't see any crosshairs, and that's because we didn't get enough successive frames of the bird path in order to form a prediction on. And I trained this on 8 instead of the 3 that I showed you in the example. There are actually 8 angles of sequence before I do the 9th predicted angle. So I was surprised that it was, okay. It gets mixed up because when I collect the contours, it can collect more than one contour if there's more than one bird. And I just randomly take the first one. So it'll switch back and forth between birds sometimes, like that. And some of these birds are so small you can't see them in the webcam video. At any rate, I'll leave you with that.